department at the University of Warwick. He's also the director of the Center for Research and Statistical Methodology and a fellow of the Royal Society.
Thank you very much. Okay, so thanks very much to the organisers for this really fantastic workshop. It's great to be here again, here in Cambridge. And I also understand that I'm the only person that's actually keeping you from a drinks reception, so I'm very conscious that I can't go over town, or I'll be very unpopular. So what I wanted to talk about today was work which I've been involved in the last sort of couple of years ago or so, which has sort of developed, and I think it's very much an ongoing development, and I thought it was ideal for this workshop in the sense that I think there's an awful lot of more practical work which really has to be done in this area, but some of the sort of important, hopefully important foundational work is stuff that I think has been quite exciting over the last few years, and this is just part of it. There's quite a few people now that are sort of involved in this kind of area. And as Michael Jordan was kindly saying this morning, that it really does resonate, a lot of this work, with some of the themes that were coming out of his work on optimization. In particular, the idea of working in continuous time turns out to be completely crucial to the kind of algorithms, these are MCMC algorithms that I'm going to be talking about, is absolutely crucial to what we're doing. Non-reversibility is a concept in Markov chains, which is not normally something which is particularly important and particularly useful for MCMC, but it turns out to be crucial for these methods. And then perhaps more to the theme of this workshop is the idea of scalability, and I'll say something quite shortly about why these methods have particular interest in terms of scalability and particular promise for future work. Okay, so this work is I'm going to basically introduce this idea of piecewise deterministic Markov processes. Last talk of the day, I'm going to try and keep this completely non-technical. There will be very few equations, but the point will be that you need these things are fairly simple objects that have been not really very well understood and not very well studied in recent years, in comparison to, for instance, diffusion processes of various types. However, it turns out that they have really quite interesting uses, as we're going to find out. And these basically, most of the talk I'm going to be presenting is this paper here on Zig-Zag super efficient sampling, which is joint work with, it doesn't say it there, but it's with Paul Fernhead and with Joris Bierkens. I also wanted to talk about something a little bit more recent. So at the end I'll say some words about some interesting theoretical questions which we've made some progress. I've said that this will be on archive very soon. I think it is actually on archive already, so that's already out of date. Okay, and the other thing is that hopefully good, accessible at least entry into this area will be an article that we're currently writing for, hopefully for statistical science, and this is joint with Paul Fernhead and a couple of other authors as well. Okay, and so the idea of super efficiency that we're talking about here is essentially in the context of large data sets. It doesn't have to be it doesn't have to be large in the conventional, well, it has to be a large data set in the sense that the computational cost of calculating the likelihood is expensive, but essentially, and I'll give a more precise definition later, this is what I'm talking about. So we're looking at algorithms, MCMC algorithms that can simulate from distributions for which the computational cost of running the entire algorithm, okay, divided by the cost of, say, one single likelihood evaluation goes to zero in some kind of big data asymptotic. Okay, so this is the idea, and this seems like an amazing thing to have, but of course one reason why you get it is because the bottom here is just very, very expensive, incredibly expensive likelihood evaluations, and we're essentially looking for algorithms which are relatively cheap in comparison to that. Okay, so that's what we're heading for. But first of all, I want to introduce this notion of piecewise deterministic Markov process. So these were introduced, well, I mean, I think they've sort of been around since around 1950 or so. But really, the mathematical foundations were only really developed by Mark Davis in a paper in RSSB in something like, oh, I should remember this, 1980 something. Really rather late for stochastic processes which are quite simple to describe. And actually, they look as if they have quite nice simple properties, although some of the mathematical complications turn out to be quite interesting. Okay, and they're easy to describe. So deterministic dynamics according to some differential equation. In practice, this differential equation will be something which we can actually solve. And when we're doing MCMC, we would be silly not to choose this to be something which isn't solvable explicitly. So we will actually choose this to be something we can actually simulate from. And then along this trajectory, you have some kind of hazard rate. And the hazard rate lambda determines events at which we basically change and jump to some other state. Okay, so simple diagram. This is what's happening really. We start off, say, here, and this is, oh, no, we don't. We start off down here. And basically we come to here, and then basically the hazard rate tells us to jump to here, and so on and so forth. So this is what a piecewise deterministic Markov process is. What can we say about such processes? I mean, they're sort of very, very strongly, very clearly non-reversible, right? They have, while they're in these kind of long deterministic trajectories here, they are clearly non-reversible. They clearly have direction, and therefore, sort of, they're not in the sort of framework of nice reversible Markov chains. However, that can still be of interest. Okay, so. They really date back to something called the telegraph process in Mark Katz in 1951. So this paper by Mark Davis, interesting enough in RSSB, even though it's really a theoretical probability paper. It's not about applications particularly. These processes are intrinsically continuous in time. Okay, you can try and discretize them. But as we'll see, actually, it's not unlike what we often do with diffusion processes, which is to start off with some continuum, which is some idealized thing we'd like to simulate from, and then discretize to use within an algorithm. We'll find that the opposite is true here. The best thing to do is to actually work in continuous time and work actually within the computer also in continuous time. Okay. So they've been pretty much understudied until recently, where there's been really sort of quite a massive growth of work in this area. And I want to just give some, just say something about the literature without going into any specifics. And most of the literature until really very recently has not been focused on Monte Carlo methods. It's not been focused on simulation of things with particular target distributions. It's very much been used in sort of various types of modeling. It's been used in certain kind of scientific modeling of various types. And there's been a lot of theoretical work recently. But certainly within the last, say, 2 or 3 years, there's been a realization that we can actually do some quite interesting things simulation-wise, and the uses of Monte Carlo. And as a result of that, the area's grown massively. Okay. And I wanted to sort of describe the uses by, returning to perhaps one of the simplest possible Markov chain Monte Carlo algorithms, and also one which is really very well understood theoretically, but just to sort of do a comparison with something which is more familiar. So this is the simplest form of something called a slice sampler Markov chain. This is an MCMC algorithm that says I'm drawing it in one dimension here. This is my one-dimensional density on the half line. I'm going to start from, say, this location here. I'm interested in simulating from this density. What I'll do instead is I'll simulate from the uniform distribution under the graph of this density, and so therefore I'll basically start off from this point, and then I'll uniformly simulate from the height, and then give me a new value here, and then I'll do a horizontal move which will be simulating essentially, if I can follow this along, simulating uniformly between this value here and 0, and in fact it produced this value here, and then if we can continue with this process and we get a trajectory of this kind. Okay, so the big black dots actually produce a Markov chain in discrete time, which has invariant distribution pi. Extremely easy to check that that is the case, and it's a nice Markov chain. In practice, this isn't a Markov chain that you can implement in interesting high-dimensional settings, and it's a pity because actually we have a complete theoretical understanding of this MCMC algorithm available, which is clearly not the case of most MCMC algorithms. However, rather than sort of look at that algorithm, I'm going to look at something slightly different. I'm going to say, maybe we can use the same picture and draw something slightly different. So now what I'm going to do is I'm going to say, instead of actually starting at some point within the epigraph of this thing here, what I'll do is, first of all, I'll choose a uniform random variable. I'll get this uniform random variable u, I'll remember it, and I will start here. And then what I will do, I will essentially have a horizontal trajectory that goes along here until it hits the function, and then what does it do? Well, essentially it just moves back again. So actually it jumps to 0, doesn't really matter if it jumps to 0 or not, and then it kind of goes back to the 0 again. Once it gets back to 0, what does it do? Well, it just throws away this uniform random variable, produces another uniform random variable, and now has another excursion. Okay? It has another excursion, and that other excursion may go further into the density, or it may go not quite as far, depending on what the value of u actually turns out to be. Now, it's also a very straightforward exercise to show that this actually gives you the right invariant distribution. Okay? Moreover, this is a continuous time object, and it has some quite nice antithetic Monte Carlo properties. Because actually, if you think about when you're actually doing this trajectory to there and then back again, actually it's sampling from the entirety of uniform distribution. So it's actually visiting each of these points. And actually, it turns out, and even though this is not really very well theoretically understood as yet, it turns out that this produces a Markov chain which has pretty quite nice, a small Monte Carlo, asymptotic Monte Carlo variances in this case. Okay, so that's an alternative, but how can we use that to construct kind of more interesting algorithms? Right, and now we're going to sort of start from somewhere slightly different. We'll come back to that picture later. Standard Metropolis Hastings, I'm actually writing everything now in discrete state spaces, at least for the time being. S is a finite set, Q is a transition probabilities, and pi is our density of interest, which is a target density, and I'm going to propose my moves according to Q, and I'm going to accept according to this probability A. Okay, so this is the standard Metropolis Hastings algorithm that's been very successful in many ways. Easy to write down what the Markov chain is. This is the transition probabilities, and the reason why it works, of course, is because it's reversible with respect to pi, and so we actually have the detailed balance relationship. Okay, so non-reversibility. So why on earth would we want to go non-reversible? If we have this beautiful framework here which allows us to produce a Markov chain which has an invariant distribution given by this global distribution pi, essentially just on the basis of local calculations involving x and where I might want to try and jump to y. So that's one of the beautiful things about Metropolis Hastings. It produces a locally computed algorithm in terms of something that, and then produces something which has an invariant distribution we want, which is a global property. Okay, and in fact, so of course, being reversible, there's very, very nice mathematical theory. Markov chain transition operator has nice properties of being self-adjoint. Its spectrum is real. If it's geometrically ergodic, which you can often prove, then you can do things like prove central limit theorems, which are useful in estimates. You can also do finite sample calculations. There's all sorts of nice things you can do specifically because you're in the reversible Markov chain case. But perhaps a more practical reason why we've always worked with reversible Markov chain Monte Carlo is that this detailed balance is a local condition, and so crucial for its implementation. You don't need to integrate anything out to decide whether to accept or reject. Okay. So why should we bother to look further? Maybe we shouldn't bother. but I wouldn't be giving this talk if the answer to that was we shouldn't. So the other side of the coin is the following, and it's sort of been known for about, I guess, best part of 30 years, that in contexts in which you can compare in some like-minded way reversible and non-reversible Markov chains, it's very common, and there are many examples, and it's somewhat anecdotal, and there isn't a big theorem, but it's occurred in many, many interesting contexts and non-pathological, that non-reversible Markov chains have actually superior convergence properties to reversible ones. And so it happens very commonly. Here's some examples here. Huang, Ma, and Xu is the first example that I'm aware of, and that does some quite kind of general Gibbs samplers on Gaussian distributions and things of this type. This is from the computer science literature, the second reference, and then third reference. But there are many others actually. So there are a number of examples where this phenomenon has been actually noticed. Okay. And in fact, I mean, so one of the most, arguably the most kind of topical current MCMC algorithm is Hamiltonian MCMC, which basically tries to construct Markov chains which have a kind of non-reversible character and then gives them an accept-reject mechanism. Actually, the usual way of implementing Hamiltonian MCMC actually then turns it into a reversible Markov chain, but so the sample paths have a kind of non-reversible character. And Hamiltonian MCMC has been rather successful, and one of the reasons it's been successful is because of this heuristic that by having some kind of non-reversibility, having some kind of momentum gives you a kind of engine to kind of move around the state space. Okay? And there is some limited theory to support that in sort of general, but not an awful lot. But this is enough information to make you think, well, maybe we should be trying to construct some generic ways of doing non-reversible MCMC. Okay, so this is a slide which might look familiar. It should do, because it's exactly the same as one before. So this was my Metropolis algorithm. Just to remind you, Q is my proposal, pi is target distribution, acceptance probability is given by this formula here. Okay. So what might I do? Well, if I wanted to actually alter this, maybe I could alter this. Now remember, I didn't start off by saying that Q had to be reversible in any sense. So Q doesn't have to be reversible at all. So if I wanted to modify this, I'd have to change the acceptance probability, right? And it turns out, and this is a nice observation of Joris Bierkens about 3 years ago, that actually you can change this quite easily if you just change the acceptance probability by adding in a skew symmetric matrix gamma here, and basically you produce a non-reversible Metropolis Hastings algorithm. Right? So this skew symmetric matrix with zero row sums, which we call a vorticity matrix, is something which in principle you can choose in arbitrary ways. So this gives a general recipe for doing this. Of course, because we've actually added this thing in, because of the skew symmetry, there's no way the reversibility, the detailed balance condition is going to hold. But it's easy to check that pi is still invariant for p. Okay, that sounds good. What's the problem? Well, the problem is, of course, to make this really work, this acceptance probability has to be a probability. Okay, and therefore gamma, this whole quantity here can't possibly go below 0. And well, you might have thought, well, that's not too bad, because I can just basically make sure it doesn't. I can just stop it until it does. Oh, I was going to show you some videos, just briefly, just to, in case. Right. This is sorry, it's not very clear here, but this is. Maybe can I run these both at the same time? No. All right. Sorry. Start again. Okay. So this is non-reversible. This is reversible Metropolis algorithm on a distribution on the discrete circle, which has kind of three modes, one mode here, one mode here, and one mode here. So it's just basically proposing to move anti-clockwise or clockwise, and you saw that basically it didn't really leave one of the modes. If I produce a non-reversible Metropolis Hastings, such as one, as in that paper by Joris Bierkens, essentially what happens is you can see the red dot, it sort of has a momentum which pushes it round anti-clockwise. And so this kind of intuition allows you to sort of at least think it might be plausible that you can get much better mixing in this case. Okay, so what's the problem? Well, the problem is that, okay, so we want to have this skew-symmetric matrix gamma, and I want basically to modify my acceptance probability. But actually the restriction that that's a probability is a very, very strong one. And so, for instance, if you look at something which is a Markov chain on, say, 4 states like this, it turns out that there are no non-reversible Markov chains which basically have invariant distribution, the thing that we started at pi, essentially. And this is kind of easy to see, and that basically means that you just cannot choose such a matrix gamma without, for some xy, violating this condition that that axy actually has to be bigger than or equal to 0. So one of the sort of very nice ideas that's been suggested in the literature in a paper by Bierkens and Holmes and Radford Neal, originally, at least in a sort of toy example, is the following idea: is to sort of duplicate my state space and basically have an independent copy here of my state space, in which basically I'm going to have different dynamics when I'm in these 4 states from when I'm in these 4 states. And this is essentially, therefore, in MCMC, you'd call it an auxiliary variable method, because essentially now you have a variable that's telling you whether you're basically in the upper set or in the lower set. But it gives you a lot more flexibility, and this is sometimes called the lifted MCMC chain. So how can we construct lifted MCMC algorithms? And there's a very sort of beautiful paper that comes out of the physics literature in 2011, which gives a general recipe for how you might try and do this. And this is the construction. But you basically do, as I said, you have your state space S, you augment it to S sharp, which gives you a +1 or a -1. And if you have 2 transition matrices, T plus and T minus. This is just in general, we're not in the Metropolis Hastings setting particularly here. And T plus and T minus are sub-Markov in the sense that they satisfy skew detail balance. So for all x, y, and z, you've got pi x, T plus xy equals pi y, T minus yx. Okay? So this allows the possibility that moving from x to y might be much more likely than moving from y to x. Okay? And basically then you have to have, well, what are these probabilities here? T minus plus and T plus minus. You've actually got to have some mechanism for moving between the 2 dynamics. And so what they do in this setting is essentially the probability, for instance, of going from the negative replica to the positive replica is essentially just given by the maximum of this, of 0, and this kind of difference here. Okay, so this is a general recipe for the sort of thing that you can kind of try and construct here, and this gives a general recipe for a non-reversible Markov chain which has invariant distribution pi. Okay, and how would you implement this for Metropolis Hastings? Well, there is a sort of an easy way of trying to do it, and there are sort of various modifications of this you could do as well. In other words, how are you going to choose T plus and T minus? Well, you might sort of say, I would like my non-reversibility to reflect a desire to move along a particular axis, defined by some one-dimensional function eta, Okay, so eta basically, essentially if I'm in the positive replica, then I essentially will want myself to basically increase eta if possible. So I'll only allow myself the bits of Q which increase eta, and correspondingly the opposite is true when I'm in T minus. Okay, so if you're in a bimodal example, for instance, what you might do is you might have some function eta which is discriminating as well as you possibly could between the two modes, or something of that kind. Okay, so skew detail balance is easy to check. This is a consequence of the ordinary MCMC detail balance, and so therefore you can construct the algorithm. Okay. Okay, so does this completely solve the problem? And the answer is no, because essentially to know what the probability of moving between the replicas, you essentially need to compute this sum. And what's this sum? This sum is over the entire state space. So that will be an integral in a continuous state space, for instance, and therefore it's not something that's going to be practically useful. Okay, so does that mean that we can't do it? Well, so this was the starting point for my work with Joris on this. And essentially what we wanted to do was, first of all, we were interested in analyzing the behavior of this particular algorithm in the limit as you looked at sort of bigger and bigger systems, as the size of the system went to infinity. Okay, I'm not going to describe that particular work, but actually one thing that came out of it was that the infinite dimensional limit that we actually ended up looking at turned out to be something that was useful algorithmically. Okay, so we studied this for the Curry-Weiss model in statistical physics, and we looked at it as a continuous time limit as we kind of speeded up in higher dimensions this particular process. And that was purely a mathematical object, but it turns out that the continuous time limit of this is something that's easy to extend to much more general target densities. Okay, and this is it, in some sense, in a very simple way. And a way to think about it is essentially the following. So in this particular algorithm, what I did was I said, well, let you be born before I even start moving. And if that's the case, well, that's fine, but I'm actually, an alternative might actually be, and again, it's very easy to check that this is completely equivalent, is to say, actually, let's move along here with a velocity +1, and let's have a hazard rate given by how quick, and the hazard rate should be high if basically the density is decreasing rapidly. Okay, so the correct hazard rate turns out to be the maximum of 0 and minus the derivative of log pi. Okay, so this gives an idea for what we might have as the algorithm, and it turns out that this formula is true in general. So you can actually apply this for any one-dimensional distribution and also for any high-dimensional distribution, any arbitrary dimensional distribution with some modifications that we'll talk about in a bit. Okay. Okay, and so you get trajectories that look like this. They sort of zigzag, one interesting feature is that as I said, the variances, Monte Carlo variances that you get from this kind of algorithm are much lower than one would expect, and we don't really have much theory to support that. So that's something that we need to understand much better, not particularly in one dimension, but obviously in more interesting cases. How do you implement this? And this is kind of important in the sense that if we're interested in super efficiency, this is going to be really where everything happens. Well, okay, so what we need to do, this is a standard trick. We basically just use thin Poisson processes. So for instance, if we have a sort of local bound like this, where basically I know that log pi prime is less than some constant c, then essentially I simulate a thin Poisson process of possible changes in direction between, in this case, my direction is either +1 or -1. Okay, I can change direction, and basically I decide to actually do that change of a direction with a probability which is the maximum of this quantity here over c and 0. Okay, so this is something which we can, in principle, we can always do that kind of calculation. And the point is, once we've got this upper bound C, basically all I need to do is simulate this Poisson process of that rate, and then just basically at each time do a likelihood evaluation from this thing here, or a posterior density evaluation, and on the basis of that basically decide whether or not to change direction. Okay, there's a lot of details of that which not so complicated, but to make it sort of reasonable and efficient. There's another slightly more complicated example of the zigzag on a Cauchy distribution, doing actually, as it happens, much better than the black density, which is a Metropolis algorithm, which is not surprising because Metropolis are known to be very poor on that density. Right. There's so multidimensional zigzag. Again, I'm not going to give you too much detail here. Here we have the basically a velocity now is given by +1 or -1 in each direction. And the switching rate of the jth direction is just given by something like this. So this is if I look at the gradient of log pi, I take the jth component, and I look at minus theta j is just that's meant to say theta, as I'm sure you can imagine. This is just the jth velocity, which is either +1 or -1. So I just do everything essentially conditionally for the jth component. And I've got sort of d of these in dimension d. I've got d of these things going on at any one time. The banana that is there, not to remind me, not to make you hungry, but just to remind me that I wanted to just show you the simplest way to demonstrate this is just to show a picture. So this is the sort of thing that, say, a two-dimensional zigzag would do, and this is running it on a sort of like a banana-shaped distribution. And the point about this is that the zigzag basically has these 2 to the d directions, and as a result of that, it can basically adapt to different regions in the space in a very natural way to basically move along kind of arms and things. So this thing kind of moves along and does that kind of thing. So that's the picture you should have in your mind for what these things look like. Okay. There's been lots of literature around that's developed about this, and I should highlight, I mean, so most of this, as I said, not particularly Monte Carlo orientated, although the bouncy particle sampler is an alternative way of doing very, very similar things which has interesting kind of related properties. And essentially what the bouncy particle sampler does is its direction is now not one of 2 to the d discrete directions, but is now continuous. There are pros and cons about using both the zigzag and the bouncy particle sampler, but they do have a lot of similarities as well. Bouncy particle is also non-reversible and is also an example of a piecewise deterministic Markov process. Okay, so subsampling. How are we going to do subsampling? Say I've got n observations. It doesn't have to be independent or anything like that. All we need to have is some kind of independent, or some kind of product decomposition of our target distribution. Remember here, x is going to be typically the parameters in a statistical context. And what I'd like to do is I'd like to do everything in such a way as to avoid basically doing a calculation involving all n of these objects every time. For instance, I'm having to decide whether to change direction in the zigzag. Remember the zigzag algorithm as I described it essentially only needed to actually interrogate the target distribution pi itself at times when it wanted to see whether the possible jump according to my Poisson process really was actually a jump. And we'd like to be able to do that in a cheap way without having to basically do an order n calculation. Okay? So we aim to be lazy and to basically not do this. And there are other things you could try on this, and and people in computational statistics, this is one of the first things you might think of, something like a pseudo-marginal Markov chain Monte Carlo approach for essentially doing this, where we essentially can't evaluate pi directly, but it turns out pseudo-marginal has very poor scaling properties. But it turns out that we can do something kind of neat, and one of the big advantages of working in continuous time is that basically we end up working all the time with log pi. Log pi has an additive structure, and it's a really sort of trivial observation, but additive structures have very simple unbiased estimators. In particular, I can get an unbiased estimator at any point x of this object here just by taking one observation. Okay, okay, and so basically this would be my zigzag switch rate normally, but I'd like to be able to replace this by an unbiased estimator. And that's what I'm going to do. And it turns out that I'm not going to try and prove this, but essentially what I do in the subsampling version of this, I do everything as I did before, except now instead of actually subsampling the entire likelihood, I essentially just basically generate some I, which is just taking one of the data at random, and then I decide to basically switch with at a rate which basically just depends on that one. So that gives me, in some sense, an order n speed up in terms of the computing time for this object here. I don't have time to go into the details of subsampling and control variates, but it turns out that crucial to actually make the whole algorithm really speed up is the fact that I need to make these estimates fairly well behaved, and actually sort of they're kind of standard sensible techniques that we can use involving control variates, which allow us to do this. And so I'm not going to describe it in detail. The detail is in the paper. But super efficiency, just to give a slightly more sort of formal definition of what I mean by this, if we call an epoch the time taken to make one function evaluation of the entire target density pi, in other words, an order n calculation, then basically the idea would be we're looking for something for which we are super efficient in the sense that the effective sample size from running the algorithm per epoch diverges. And this is just an example in various simple cases. This is 100 data points, this is 10,000 data points. And just to explain what's happening here, basically the ones at the top have all started fairly close to the where we know the sort of the mass of the posterior distribution is. The ones at the bottom started further away. And every red circle here is essentially represents an epoch. So in the time it's taken that continuous time Markov chain to work out it needs to go that distance, basically it could have done one full likelihood evaluation. Okay, so this is the pure zigzag with no subsampling. So you see these red circles extremely close to each other. So it's basically costing you an awful lot. This is the basic zigzag, and this is the zigzag which with control variates. And you can't really see much advantage this one over this one until you actually look at the bigger data sets. And in the bigger data sets you can see there's loads and loads and loads of these kind of red circles here, so that's very expensive. Whereas as soon as we get to the control variate method here, actually you get all the way into the mass of a distribution before you even expend the amount of computing needed to evaluate the likelihood once. Okay. And that's a diagram showing the same thing over larger and more sort of data sets. So the algorithm I'm talking about, the control variate zigzag, subsampling zigzag, is essentially this purple one here. Okay, so this is a slightly embarrassing question to ask. This is the last part of my talk. Embarrassing question to ask, does it actually work? Is it actually an ergodic Markov chain? And this is something that we've been working on. This is much more of a theoretical piece of work, but something we've been working on for a while. There is actually a very easy way of making sure that the zigzag really is always ergodic. But actually, by doing that, it turns out that we make the non-reversible character of the Markov chain diminish. So you make it look a little bit more reversible. So it's something we didn't want to do. So we wanted to actually prove that actually the zigzag itself was ergodic. And this is actually a non-trivial question, because actually if you look at other algorithms of this type, in particular the bouncy particle sampler, it turns out to be non-ergodic in very, very simple, straightforward cases. Yeah, so I guess I haven't got time to go through all that. That's just ways in which you can fix this if you really had to, but we don't want to. We want to actually prove that the pure zigzag process itself is always ergodic. And here's, I think it's a fascinating counterexample to show that actually you can produce cases in which it's not. Here's a density, two-dimensional density, sorry, there should be an e there, e to the minus the maximum of x and y. And essentially what happens here is the zigzag has the property that if you start it going sort of anti-clockwise, then it carries on being anti-clockwise for all time. And conversely, it will go clockwise if you start it clockwise. And it's easy to sort of check that that's what happens. So it's not actually going to be ergodic, because you'll never be able to get from the clockwise configurations to the anti-clockwise ones. It's interesting. It's one reason why it's a fascinating example is because if you try and produce kind of slightly less symmetric examples, like for instance by smoothing off the contours here, you suddenly make it ergodic. So this is just an example where this ergodicity kind of can fail, but you can't produce a large class of distributions on which this thing happens. So that's kind of an interesting thing that we sort of discovered. But the other thing that can go wrong, and it was one of these annoying mathematical problems, is that if you have distributions which have ridges like this, it's quite possible for the Markov chain to basically just essentially go off to infinity along one of these ridges, and obviously it's not going to be ergodic in that case. So this is the result that we came up with, and the proof is quite complicated, and we found it quite fun. There may well be something a lot more direct. Essentially, if you've got some smoothness, and if pi doesn't, pi basically goes to 0 in the tails, and then this third condition, which is not a strong condition, but it's a slightly unusual condition, it says that the density pi has at least one non-degenerate local maximum. And what do I mean by that? In other words, if I look at the Hessian at that local maximum, that Hessian should be strictly negative definite. Okay. And then in that case, you can show that you have the required irreducibility and ergodicity from basically from all starting points.
So don't you need like minus log 5 times to be bounded, or because in your algorithm you were assuming there was an an upper bound on your minus log 5 times?
Sorry, I didn't hear the first part of that.
So you don't need to have minus the derivative of log pi to be bounded, because it seems to be one of the things you use in the algorithm.
No, so all you need is for that. I mean, so the fact that you've got the C3 condition means that it's going to be locally bounded. This is one of the big advantages over diffusion algorithms, because diffusion algorithms always, even in a very small time, have a positive probability of going arbitrarily large distances. You've got this kind of maximum velocity of +1, -1. So actually, you can do all of this in a local way, and computationally cheaply as well. It's not going to be a problem at all. But that's a very good point, actually, and that actually this is much more robust than things which are based on sort of diffusion type algorithms.
How does this rule out the example with the ridge? Is this because of the second condition?
Oh, yes, second condition, yeah. Okay, and since people seem to be very interested in this, this third condition. Essentially, it took us probably about a year to prove the result for Gaussian densities. And essentially, condition 3 All this is saying is that basically you can produce some kind of very, very local, in a very, very, very small region around this local maximum, you can actually produce Gaussian approximation, which allows you to sort of move around and maneuver in that sort of small region, and then you can go everywhere else. So that's essentially the proof. Okay, so I'll just put this on quickly. I hope I've convinced you that these piecewise deterministic Markov processes are fun, they're interesting, they're not too complicated, and they have some uses. The subsampling and control variance actually gives quite big computational advantages in terms of situations like large data. We do need this. There's a lot of interesting kind of theoretical stuff we still need to do, as well as, of course, more practical stuff. But I think if the Zig-Zag and the bouncy particle sampler and other piecewise deterministic Markov processes, I think they offer sort of lots of promise for applications in lots of situations, especially large scalable problems in the future. And also, just it's something that's interesting is that there are connections to Hamiltonian MCMC and clear improvements on Hamiltonian MCMC in some contexts, but probably not in all. And we don't know much at all about this yet. Okay. So thank you very much.
This smoothness condition, this C3 condition, is this necessary? Or, I mean, what if you have a discontinuous... I mean, high-dimensional applications, it can be of interest that the posterior is actually discontinuous. So.
Okay, so good question. So the C3 condition, almost certainly not. I mean, I imagine you just need a C2 condition. And you need C2 condition to make this Gaussian thing work. But probably we could push that to, I don't know. I'm just guessing here, but C2 plus epsilon or something like that. Yeah, I imagine that could be weak.
If you have a discontinuous density, are there some counterexamples?
Oh yes, so a discontinuous densities all sorts of bets are off, because this one here actually has this is a continuous density. It's not C1, right? Okay, so and you get this. Although there may be other ways of stopping this kind of counterexample, but actually it's not obvious. And you can sort of see that in this example. You know, this does not have a mode which behaves nicely in any sense, right? So you can see this. But obviously there's a gap between the C1 that this isn't and the C3 that the theorem, yeah? So there probably is, I imagine you can get away with C2 plus epsilon or something of that type. Yeah.
Is there a possibility, can you explain us maybe shortly, I don't know if it's possible, the intuition to have this kind of magic condition that says like locally you're good and so you're good everywhere to get... Because it's a bit like this third condition tells us. It's a bit
yeah, okay. So I think so. Intuition. So if you can prove, right? So I guess what this is saying is so we have this condition 3 mysterious. So you've got this big state space here. It's got one local maximum here. Locally, this looks Gaussian, right? So you can find admissible paths basically anywhere around here, anywhere very, very close. I've tried to draw 2 points very close to each other, if you can see them there. You can actually get from any point there to any other point, and in particular, you can do it in such a way that the velocity changes to whatever you want it to be. So if you want to get somewhere in the state space like there, then essentially what you have to do is you have to sort of move to wherever you want to be and then position yourself to be able to move there. So you can so basically the algorithm involves basically saying, well, so if you start somewhere like that, then all you need to do is show that you can get into here. The problem is that, I mean, even in that counterexample, you can actually get everywhere in the state space, but you can't get everywhere in a way such that the velocity is doing the right thing. So it's easy to sort of say that you can get into here, but actually you can't get into here with any direction necessary. So when you go into here, and then because the Gaussian result, you can actually change direction to whatever you want, and then you essentially apply it, since you apply that argument in reverse to basically say you can get here. So therefore you can go from here to here, but you have to go via there. So it's completely non-direct proof. The Gaussian thing is complete red herring. I don't really believe there's anything Gaussian that's intrinsically important to this result. But the Gaussian proof is hard enough and we couldn't find a more general kind of way to do it. The Gaussian is quite an involved calculation in its own right.